Hello everyone, my name is Farhan and I'll be going through the Math 2018 crash course for today. Firstly, I'll quickly go through a topic breakdown. So in total there's 9 topics. The first 6 of these topics are actually quite short, and they're pretty much just a revision from Math 1A, 1B. However, these last few, topics 7, 8, 9, are completely new, and they're a bit longer as well. They've got double the amount of lectures as what we seen in the first 6 topics. Okay. Usually topic 4 and topic 8, double integration and Fourier series, are the most difficult questions that we get in the exam, and the actual content is also pretty difficult. However, everything else, 1 to 3 are pretty simple. 5 is straight from Math 1A and 1B. Same with topic number 6. Laplace transform and partial differential equations are moderately difficult topics. So I'll write this down as moderately difficult. Laplace transform can get hard. However, the actual content is pretty simple. And for partial differential equations, it's really repetitive. So once you pretty much know the fundamentals of one question, you'll be able to do every single question from now on. And it uses content from topic 8. Okay, let's get started with, I'll be going through topics. Which topics will I go through today? I'll be going through, mark this down, topic 1, 2, and 5. I'll be going through these 3. Okay. Topic number 1, we start with the functions of several variables. Topic 1. In this topic, there are 4 lectures or 4 aspects to it. The first part is partial differentiation revision from Math 1B and graphing functions with 2 variables. So an example would be graphing a plane or graphing a sphere. So z squared plus x squared plus y squared is equal to 5 or 25, something like this. This would be a sphere. 2 variables, 3 variables, something like that. I'll just say several variables. Several. Okay. Part 2 is a chain rule and a bit more revision from 1B. Taylor series. Taylor series we saw in Math 1A, but we only saw the very simple one, the simple version with 1 variable. So something like this. What does it look like? Take a look. I forgot what it looks like. Okay, that's fine. But over here we'll be doing Taylor series for functions of 2 variables. In this course, I'm going to be looking at 2 variables and the maximum 2 variables. 3 variables and onwards would be much harder and not assessed in this course. Leibniz rule is a completely new topic that we haven't seen at all, but it's probably the easiest out of all the 3 up here. Okay, let's move on to partial differentiation. This is the definition of a partial different derivative. However, they never ask you to answer a question using these definitions. It's always very simple, as we see in Math 1B. And rather than using this definition over here, we just use these notations. So the partial differential of z with respect to x would be denoted with a z with a subscript of x, and then if it's with respect to y, it would be a z with a subscript of y. Okay, similarly, if we were looking at the partial differential of f with respect to x, this would be denoted with an f with a subscript of x. Okay, let's move on to an example. There's really not much content to partial differentiation. Okay, so find the partial differential of w with respect to u and with respect to v if w is equal to this equation over here, function over here. Okay, so w is equal to u cubed v to the 4 plus sine of v to the power of 9. Okay. When we're differentiating with respect to u, partial differentiating with respect to u, we don't have to use product rule in this case over here. We can treat the v term as a constant. So for example, if we're taking a look at d on dx, so this is just the normal derivative of ax squared, for example. This would be the same, this would be equal to 2ax. So we see that this is the constant over here, and we can treat this v as a constant as well. Right? We can take the a to the outside, so we get a over here. Sorry, just get it to be a times d on dx of x squared. Okay, so in this case, partial differential of w with respect to u would be equal to the v to the power of 4 times the partial differential of u cubed with respect to u. And then because this term over here, sine v to the power of 9, doesn't have a u term in it, we can treat it like a constant, and when you differentiate a constant, you just get 0. So you just get plus 0 over here. So completing this derivative, we get 3u squared times v to the power of 4. Okay. Similarly, when we differentiate with respect to v, we can treat the u as a constant. So you get u cubed times the partial differential of v to the power of 4 with respect to v. And then now we do have to differentiate the sine v to the power of 9 because we're differentiating with respect to v. So over here we'd get 9v to the power of 8 times cos v to the power of 9. Okay. Completing this, we get 4u cubed v cubed plus 9v to the power of 8 cos v to the power of 9. So those are our two answers. Okay. It should be pretty simple. We did this all throughout Math 1B. Okay. This is a more difficult, not difficult, but I'd say more, how do I say it? An application of partial differentiation where you're trying to find the gradient in a certain direction at a certain point as well. Okay. So if we have z is equal to f of x y, which is equal to x cubed y squared plus cos of pi x plus 3y minus 2, and we want to find the rate of change in the x direction. So whenever we're talking about rate of change, first of all, we're always talking about the derivative of f. Okay, this is true in normal differentiation as well, not just partial differentiation. The only difference is that in partial differentiation we have to be careful of which direction the rate of change is. So in this case, we're talking about the rate of change in the x direction, so we're going to have to partial differentiate with respect to x. Okay, so I'm going to write zx is equal to 3x squared y squared minus pi sine of pi x plus 0 minus 0. Okay, these terms just cancel out. So 3x squared y squared minus pi sine of pi x. Okay, but we're not done yet. We're trying to find the rate of change at a certain point. Okay, So all we need to do now is just substitute in this point. So z of x at 1, 2 is equal to 3 times 1 squared times 2 squared minus pi sine of pi. So sine of pi is just equal to 0. So we can cancel this out. And this just becomes 12. So the rate of change of f in the x direction at the point 1, 2 is equal to 12. Just a small application of partial differentiation. Okay. I'm going to move on to plotting functions of several variables now. This is when I was talking about graphing graphing functions with several variables. Okay, so first of all, a plane. Okay, whenever we're graphing a plane, the way to do it is that we want to find the x, y, and z intercepts. Okay, and it'll look something like this. Let me take a look. Okay, so where there'll be like a intercept here or here and here. Right. So this is the equation. This is for a plane. Okay, for a sphere, it will look something like this. Oh, this is z, y, and x-axis. Z, y, x. Just looks something like that. When we're drawing this 3D shape, we can just draw it as a circle and then add these two lines to show it's 3D. A cylinder, however, is very similar to the equation of a sphere, but we're just missing the z term over here. Okay, what the cylinder is it's a circle in the 2D plane, but it's extended infinitely in the z plane. So I'll write that down. 2D in circle in 2D slash xy plane, but it's extended infinitely in the z direction, and it looks something like this. So this is a circle in the xy plane, and it's being infinitely extended. Oops. And it's being infinitely extended in the z plane. Okay. The next shape that they ask us to draw are cones. So in polar coordinates, we know that r squared is equal to x squared plus y squared. Right? So we can write the cone equation as z is equal to a times r. Okay? And if we sketch this in the zr plane, so a zr plane, we just get a straight line. Okay? So it's just a linear line, but because it's in polar coordinates, if we want to draw it in a xyz plane, we're going to have to rotate it about the z-axis. So it will look something like this. Do it in a different color. Looks something like that. And then it will be rotated around the z-plane. And when you look at it from the top, it looks like a circle. Okay, that's why we have this circle cross-section over here. Z, Y, X. The next two shapes that we're asked to look at, the next shape, sorry, there's only one more shape, is a paraboloid. So it's very similar to what we've seen with a cone, except we don't have the square root. Okay, that means in polar form, our z is equal to ar squared, which in the zr plane looks just like a parabola. Okay, and what we want to do is rotate it about the z-axis, so it looks something like this. Okay, it looks something like this. Not too bad. I've added one more over here. This is for x is equal to y squared plus z squared. Okay, firstly we looked at z is equal to a times x squared plus y squared, and we can see that the paraboloid is true for all positive values of z. Okay, and for the one that I've added down here, it's true for only all x values, all positive x values. Okay, so that means it will be pointing, I'll draw it over here, it will be pointing towards the x direction rather than the y direction. So it will look something like this. Okay, I'll draw it a bit nicely. Okay, so this is x is equal to y squared plus z squared. Okay, and up here is z is equal to a x squared plus y squared. The a is just a constant, by the way, so it can be any number. Okay. If it was a negative, that means we just flip it across the what would it be, xy axis. Okay. So it would look something like that, down this way. That's the z-axis going negative. Okay. Okay. Now I've got a few questions here. Part A, as I've said, so we know this is a plane first of all. It follows the form of the plane. Ax plus by plus cd is equal to d. Oh, actually, this should be cz. Sorry, it should be a cz. Cz, not a cd. Okay. Now, the way to do this type of question, first of all, and also one more thing to note, up here, we know this is a circle. This thing over here is the radius. That's the radius down there. I was going a different color. That is the radius. Okay. First question. We want to find the x, y, and z intercepts. So let's let x equal to y, which is equal to 0. Now what that does is that we get rid of these two terms and we can find the z-intercept. Okay, so therefore z will equal to 12 divided by 6, which is 2. Now let x equal to z, which is equal to 0. For this one, we can cancel this one and this one out, and we can find the y-intercept now. So y will equal to 12 divided by 4, which is 3. Finally, the x-intercept. Let z equal to y, which is equal to 0. X will equal to 4. Okay, so these ones are our intercepts. So when we sketch this out, in the z-axis we'll have z is equal to 2 somewhere here, y is equal to 3 here, and x is equal to 4 somewhere here. Then connecting these all together, actually I'll do it properly. We get that to be our plane. That thing over here. Okay, and this extends infinitely outwards as well. I've just restricted it to the first quadrant, octant. Sorry. So this is z, y, and x. It's a bit easier to draw it this way, and it's easier for the marker to understand as well what you're trying to draw. Rather than drawing a plane like this, it's hard to show where the intercepts actually are. Okay. Part B, that's just a sphere with radius 5. So I've actually done this somewhere up here, over here. Yeah, up here, right? X squared plus y squared plus z squared is equal to 25. When we want to sketch this out, B, so when this is a sphere with radius 5, you get something like this. Okay, and then you can just denote your radius. So if this is the center point, you can just denote your radius like this. 5. So r is equal to 5. Okay. Oh, actually no, sorry. In this case, the center is actually at the origin, so that's incorrect. So what I'll do, I'll move this down a little. The center is at the origin over here, so that means this will be the radius equal to 5. Okay. However, if we were given something like this, x minus a, all squared plus y minus b, all squared plus z minus c, all squared is equal to r squared, our radius would be r, but our center would change to a, b, and c. Okay, because it's being shifted to the right by a, to the right by b, and to the right by c. Okay. Next question. We are drawing x squared plus y squared is equal to 9. So this is a cylinder. Give me a sec. This is a cylinder. Cylinder with radius 3, extending infinitely in the z direction. The z direction. So it looks something like this. X, Z, Y, and it's also centered at the origin. So okay. I'll draw it like this. Okay, that's a bit better. So it looks something like that, and then dot 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 all the way down to show that it's being extended infinitely towards in the z direction, both in positive and negative z direction. So I can extend this downwards as well, like that. Okay. Part D, we're drawing a cone. So in polar form, this is just 3r. Okay. So when we're drawing this cone, there's no special way to draw it. X, Y, Z. Just draw something like this, something like that, and then maybe add something like that. Okay, and that shows that it's a cone. And then maybe you can add something at the top here as well. They don't usually ask you to graph these in the exam, because the exam's on Mobius. So they'll probably give you an equation like this and ask you to identify which graph is correct. So they probably give you like a multiple choice question like that. Okay. Over here we've got a paraboloid. So both of these, the last two are actually both paraboloids, so I'll draw them in the same E/F. I'll draw them in the same axes, but I'll just make it a bit larger. X, Y, Z. So our first one, draw something like that. Okay, that's much better. Like that, and maybe if you want to add something like this as well. Okay, it doesn't hurt to add it. So this is the equation, z is equal to x squared plus y squared. If we had a plus 1 at the end here, this whole graph would just shift up by 1. So this would be at 0.1. Okay. Now I'll draw the second one as well. So as I said earlier, because we're taking a look at x is equal to y squared plus z squared, this is only true for all positive x values. And a way we can interpret that is because y squared and z squared are both positive always because of the squared, and therefore the right hand side will always be a positive number. It can never be negative. It can be 0, but it can't be negative. So it will look something like this. Okay, pretty chill. Okay, let's move on to the chain rule now. Okay, the chain rule for functions of more than one variable. So if we have z being a function of x and y, and we know that x is a function of t and y is a function of t, so it's pretty much a function within a function, essentially, right? So what we've dealt with before was y is equal to f of x, where x is equal to x of t, right? And that's pretty simple. Dy on dx is equal to, sorry, dy on dt would be, sorry, I'll just rewrite that. Dy on dt would be dy on dx times dx on dt. Pretty simple. And then the dx's cancel out and you get dy on dt. However, for something with two variables, you're going to have to consider two differentials, okay, and then add them together. Okay? I think in 1B they taught you this with a tree diagram sort of thing. So dz on dt. We have x and y. Yeah, and then from here you have dx on, sorry. No, that's incorrect. That's fine. You can just use this formula over here, okay? And now a new equation that we get, this probably isn't that new, but this one's I'm pretty sure is pretty new. When you have two variables, f of x and y, and your x and y are also functions of two variables, okay? You're gonna have to use two different equations to find two different differentials, okay? In this case, we only need one because our x and y are just functions of one variable. However, in this case, x and y are functions of two variables, so we need two equations, okay? It's usually more effective to use a chain rule than to calculate the new function. Yeah, absolutely. Because you might get some whack function like x is equal to, if it's in terms of u and v, you might get like cosh u to the power of e to the power of u, something like that, right? Something ridiculous. And then they might get like y is equal to sine ln of v, something like that. And then if f is equal to x squared plus y to the power of pi, right, then it gets really, really cooked, right? It's better to just separate the, calculate them separately and then add them together right at the very end, okay? Hey, given that z is equal to x squared plus y cubed, with x is equal to 2t and y is equal to sine 4t, use a chain rule to find dz on dt. Okay, so this is using this first one over here. Okay, let's quickly give this a go. So first of all, I'm gonna find dz of dx, which we get to be 2xy cubed. Dz of dy, we get to be 3x squared y squared. Alright, then we're also going to have to calculate dx on dt and dy on dt. Okay, for this we get 2, for this we get 4 cos 4t. Okay, and now dz on dt is equal to delta z on delta x times dx on dt plus delta z on delta y dot dy on dt. Right? Substituting everything together, we just get 4xy cubed plus 12x squared y squared cos 4t. Final answer. It might be a little blurry, that's fine. Okay. And you can also verify your answer by doing by substituting it in separately and then finding your answer the long way. But this, using the chain rule, saves us a lot more time. Okay. The second question. Now, in this case, we know that w is a function of a and b. However, a is a function of u and v. So our a and b are functions of two variables, and that's the same with our w as well. And in this case, we're actually trying to find it at a certain point. Okay, so the way we're going to do this, dw on du, that's what we're trying to find, du. So we're only using this one over here. Okay, if they ask us to find dz on du as well, then we'll also have to use this. Okay, however, because they're only asking it with respect to u, we're going to have to use the first equation. Okay, now we know that w is a function of a and b, and what is this? A and b is a function of u and v. Right? So for w, we're going to have to partial diff both a and b, and then to find it with respect to u, we're going to have to partial differentiate a and b only with respect to u. Okay, I'll show you what that looks like. So delta w over delta a dot delta a over delta u plus delta w over delta b dot delta b over delta u. Okay, so we shouldn't have any delta v terms in our equation here. The reason being is because we only want everything in terms of u. Okay, so trying to find these, we get 2a minus b cubed dot v e to the uv plus what is it, 3 times delta b over delta u. That's not right. This should be minus 3ab squared times 3. Okay. Now we also know that a and b are in terms of u and v, so we can substitute these into here as well. So we get 2e to the uv minus 3u plus 2v to the power of 3 times v e to the uv minus 9a, which is e to the power of u times v, times 3u plus 2v all squared. And now all we can do is sub in u and v. So sub u is equal to 0, v is equal to 1. Okay, what we get is that this becomes 1. This becomes 0 over here, so we get 2 cubed. So we get 2 times 1 minus 0 plus 2 cubed times 1 times 1, the the e to the power of 0 it just becomes a 1, times 9 times 1 times 3, 0 plus 2 squared. And your answer becomes, let me take a look, minus 42. Okay? That's our final answer. What you could have done alternatively is that you could have found, so alternatively, find a and b at u equals to 0 and v equals to 1, and then instead of subbing it a and b into this equation, you could have just subbed in a and b, the values of a and b, straight into this equation, and you would have gotten the same answer. Okay, so you probably would have done something like, so first of all, at u equals to 0 and v is equal to 1, a is equal to 1, and then b will be equal to 2. So what you would do is that you would sub in 1 here, 2 here, 1 here times 2 squared, this would be cubed, times 3, and you'd get the same answer as well. Okay? Alright, Taylor series and error estimation. So we've seen Taylor series with for functions with 1 variables, however we haven't seen them for 2 variables. Okay? In this course, they don't really ask us anything higher than second order. They do say plus higher order terms, but they never ask it beyond this point over here. So we're always doing questions between here and here. Okay? So this is second order, because the partial derivative of f, the highest order is the second order. That's pretty much why. Okay? So the best way to explain this is through an example. So we have f of x, y. Okay? I'm gonna pretty much just copy down what we have over here. Okay? So this is just f of a, b plus x minus a, fx of a, b. Right, what this is the partial derivative of f with respect to x at the point 1, 2. Okay. Then plus y minus b, fy, a, b. In this case, a and b is just 1, 2. Okay. Then plus, it's over, 1 over 2 factorial times x minus a all squared, f, the second partial derivative of x, a, b. So this is just the same as this. Then I would add or minus add 2x minus a, y minus b, f of x, y of a, b, plus y minus b all squared, f of y, y, a, b. Okay. Alright, what I'm going to do to make this question easier, rather than substituting everything in at once, I'm going to do it part by part, and I'm going to sub them in together right at the very end. So f of ab, which is just f of 1, 2, is equal to, so this is our function over here, f1, 2 is just 8, right? F of x, xy, or f of x, so the first partial diff is just 4x cubed y cubed, and if we sub in 1, 2, we get it to be 4 times 8, which is 32. Fy, we get it to be 3x to the 4y squared. If we substitute our values, we get 12. Next, moving on to the second order, fxx of fxx. Is that right? Yeah, that is right. 12x squared y cubed. Substituting 1, 2, we just get 96. fxy, we get to be 12x cubed y squared. Substituting 1, 2, we get it to be, what is that? 48. And then finally, fyy, we get it to be 6x to the 4 y. fyy of 1, 2 is equal to 12. Cool. Now, all we have to do now is sub into this huge equation. Okay. Now I'm going to do that real quick. So I'm going to get f of xy fxy is equal to 8 plus what do we get? X minus 1 times 32 plus y minus 2 times 12 plus a half times x minus 1 all squared times 96 plus 2 times x minus 1 y minus 2 times 48 plus what is that? Y minus 2 all squared times 12. Okay, so over here we have the first partial diff with respect to x at the point of 1, 2. Over here it's with respect to y, and over here it's double, what is it called? The double derivative, second derivative. This one is the mixed derivative, and this one is the double derivative of second derivative of y, of f with respect to y. Okay, and you can clean this up even more if you want, but I'll just leave it like this. It's still correct. Okay. Okay. Let's move on to error estimates. Okay. So the first three terms of the Taylor series are a linear approximation of fxy. Okay. So what we call it, so this Taylor series of the first three terms, we call it an approximation near AB. So we call it a Taylor series approximation near AB. Okay, and now the reason we can call it that is because we can use the Taylor series to approximate values near AB. Okay, it will work best for the values of AB, but anything near AB will work really, really well as well. So we can use to approximate or estimate, that's probably a better word, estimate values of f. Okay, and now this is an equation that you've seen in Math 1B as well. Okay, I'll quickly go through two questions, and that's pretty much as hard as it gets essentially. Okay, suppose that t is given by x squared plus y cubed, x squared plus y cubed. Find the approximate error in t if x is equal to 1 and y is equal to 2. So pretty much just treating a and b as 1, 2. Okay. So pretty much, what would be delta t delta t is equal to t of x at 1, 2 times delta x plus t of y at 1, 2 times delta y. Okay, what this course pretty much is just using equations. Okay, there's not really much to understand. It's just being able to use the equations that they give us, and there will be a formula sheet in the finals, so you guys should be fine. First of all, let's find tx, which is 2x. Ty is equal to 3y squared. So if I say at, where is that, 1, 2, we get it equal to, what is it equal to? It's equal to 2. At 1, 2, it's equal to 12. Okay, so all we're going to do here is 2 times 0.1 plus 12 times negative 0.3. Okay. And combining these, we get minus 3.4. So this gives us an approximate error if our delta x is equal to 0.1 and delta y is equal to negative 0.3. Okay. Now, this just gives us an approximate error of f, but it doesn't give us the maximum error. Okay. The maximum error is something we can find when we absolute value the values of delta x, delta y, and also the partial differentials as well. Okay. This, I think it comes from the triangle inequality. I forgot what it looks like, something like this. Yeah, something like that. Okay. And intuitively it does make sense, because if you make the changes positive, the change in x and change in y, then we can find the maximum possible error. I've just repeated what they've said here, but okay, that's fine. So first of all, we're going to find absolute error, relative absolute error, and percentage absolute error. Okay, first of all, absolute error is just delta f or delta t. All right, the relative where is it? The relative absolute error is delta t divided by t. Right, that's at the values of a and b. And the percentage absolute error is just the same as the relative absolute error, but just multiplied by 100. Okay. So part A, the absolute error, let's find that first. This is equal to fx of 1, 2 times delta x plus fy of 1, 2 at delta y. So we use pretty much, it's the same equation and the same point. So we're using the values from above. So we know that fx of 1, 2 is equal to 2, fy of 1, 2 is equal to 12. Okay, and in this case, this will equal to 0.1, this will equal to 0.3. Okay, so this is equal to, let's say, 2 times 0.1 plus 0.3 times 12, which is equal to 3.8. So this is the absolute error. The relative error, part B, first of all, we're going to find t of 1, 2, which is equal to 1 squared plus 2 cubed, is equal to 9. Delta t over t is equal to 3.8 divided by 9, which is 0.42. The percentage error is just 42%. It's the same as part B, except expressed as a percentage. Okay? So it's still recording. Yeah, okay, good. If it wasn't recording, that'd be bad. Okay. So most of this I've kind of sped through because it's just an revision of Math 1B. However, this is a very new concept that we've never seen before. The Leibniz rule. Pretty much when we're pretty much just differentiating an integral. When you're integrating a function with two variables, you're integrating with respect to one variable, but you're differentiating with respect to another variable. So in this case, we have f of xt. We're integrating with respect to t. However, we're differentiating with respect to x. Okay. There is a few conditions. Is that the v and u, the functions in the limits, they can be functions, by the way. They don't have to be numbers. The functions have to be in terms of x. Okay. Or else it would be, if it was in terms of t, then it would be something along the lines of the fundamental theorem of calculus or something. I forgot what it's called. But yeah, I'll just explain it with an example. So they've taught us find this, but do it directly first and then use Leibniz rule. Okay, so I'll do it directly. So let's integrate from 1 to 2x of x to the 6 t squared dt. What you get is x to the power of 6 t cubed on 3 1 to 2x. Because we're pretty much differentiating, integrating with respect to t, we can treat the x function as a constant, right? So this is just equal to x to the power of 6 8x cubed over 3 minus 1 over 3. And this is just equal to 8x to the power of 9 over 3 minus x to the 6 over 3. Now we're just going to differentiate this. We just get 24x to the power of 8 minus 2x to the power of 5. Okay, so technically, when we're using the Leibniz rule, we should get an answer like this. Okay, so let's do that. So this is the Leibniz rule. D on d dx 1 to x 6t squared dt. So just following the formula from above, 1 to x of partial derivative of x to the 6t squared dt. Now what I'll do, I'll move all of this over here and move this over here, plus f of x 2x. So this is just over here. Instead of t, we're substituting the upper limit, which is v of x. Okay. Same thing over here. Instead of t, instead of it being f of xt, we're replacing t with the functions in the limit. Okay. So this one over here, we have the 2x. First of all, we're going to multiply that by dv on dx, and then minus f of x 1 times du on dx. Okay, so first of all, du on dx is just 0, so this term completely cancels out, and this over here is just a 2 because dv on dx is just equal to 2. Okay, so when we finish the partial derivative, we just get 6x to the 5 t squared dt plus 4x to the power of 8 times 2 minus 0. So I'll just leave it like that. And the way I get this is x to the power of 6 times 2x all squared. You get 4x to the power of 8. Okay, now let's do this properly. 5 t cubed on 3 2x1 plus 8x to the power of 8. Okay, this gives us 6x to the power of 5 times 8t cubed over 3 minus 1 over 3 plus 8x to the power of 8. And then after you simplify everything, dot dot dot, you end up getting 24x to the power of 8 minus 2x to the power of 5. Okay. So you do end up getting the same answer. However, in this case, using the Leibniz rule is very tedious. It's much quicker to do something like that. Okay. However, there are some cases where you have to use Leibniz rule. Okay. So for something like this, we actually don't know how to integrate this at all. Okay. So if you wanted to integrate it directly at the level that we're at right now, we actually don't know how to integrate it. So we have to use the Leibniz rule. So let's do that real quick. D on dx of sine tx divided by t dt. This is equal to, between root x and x, the partial derivative of sine tx over t dt plus f of x times dv on dx, where v of x is equal to x, u of x is equal to root x, okay? And plus, minus f of x root x times du on dx. So dv on dx is just equal to 1, du on dx is equal to 1 over root x, 1 over 2 root x. Okay. Okay, when we partially differentiate this, we can ignore the t at the bottom, right? And we're just pretty much just differentiating the sine tx with respect to x. Okay, so what happens is that the t actually comes out and it cancels out with the t over here. So in fact you get something like this, x, so you get t sine of, not sine, it should be cos. It should be cos of tx divided by t dt. That's through partially differentiating the sine tx with respect to x, and these t's actually cancel out. So what you're left with is just cos tx. Okay, I'm gonna finish off the rest of this line. You get sine of x squared divided by x times 2 times 1, then minus sine of x root x over root x times 1 over 2 root x. Okay, so we're integrating cos of tx dt plus sine of x squared over x minus sine of x root x over 2x. This is equal to cos of sine of tx all over x between root x and x plus sine x squared over x minus sine. Okay. Now, evaluating this integral over here, we end up getting sine of x squared divided by x minus sine of x root x with respect divided by 2x plus sine of x squared over x minus sine of x root x all over 2x. So we have this being a like term and this being a like term. So combining everything together, we pretty much just end up with 2 sine of x squared divided by x minus 3 sine of x root x divided by 2, and that's our answer. Okay. So it is still a bit long, but there's not anything too difficult. The only difficult part would probably be the partially differentiating that sine tx. You might get a bit tripped up. Everything else is just substituting in. Okay. And then algebra. That's pretty much it. Okay. Now, scalar fields. So this is topic number 2. I'm going to briefly go over this. Okay. Oh, so this should be scalar fields as well. Okay. So scalar fields has 4 subtopics or 4 lectures, right? The way they go over it is they assign 1 lecture per one of these subtopics, and later on, also as I said before, between topic 1 and 6 is quite short. It's always 4 lectures, right? But then from 7 to 9, they actually have 8 lectures, so it is a bit longer. But the difficulty doesn't really change. It stays pretty constant. So 2.1, extreme values. So this is talking about critical points. Such as maximum, minimum, and you'll see a new one called a saddle point. Lagrange multipliers, it's just an extended version of extreme values. Gradient and directional derivative isn't too hard either. It's just using the equation. Okay, and this I'll just briefly touch on, not too much. Okay, 2.1, extreme values. So there's something called the second derivative test. This is to test whether critical points are maximum or a minimum or a saddle point. Okay. Okay. So this I'll pretty much quickly explain over here. So a geometrical description of extrema for z is equal to fxy. So you can, as we've seen, so this is for 2 variables. Okay, if we take a look at something simpler, so y is equal to fx, right? You might see something like this, right? A very simple curve with a maximum point here and a minimum point over here. So at the maximum point, we know that f dash is equal to 0. So at any stationary point, f dash is equal to 0. The only thing that is different between these two is f double dash. Over here, it's less than 0, so it's concave down. Therefore, it's a maximum. And over here, f double dash is greater than 0, so it's a minimum, or concave up. Okay, that's one way to think about it. So a concave up always has a minimum. Concave down always has a maximum. Okay. However, when we switch to 2 variables, it gets a bit different. Okay. So for function f(x,y), okay, these are pretty much just the steps to doing these questions. Okay, you want to look for critical points, and the way you want to do this is you want to let the first partial derivative with respect to x equal to 0, and fy is equal to 0 as well. So you want both of them to equal to 0. Okay. In some cases, you might need simultaneous equations to find the values of x and y. Okay. The second step is to use second derivative test. Derivative, how do you spell that? Derivative test to classify. So we're going to classify it as either a min or a max or a saddle point. Okay, I'm going to firstly talk about maximum minimums. So let's take a look at local max / min. Okay, so the way you want to think about maximum, minimums, and saddle points is you want to think about it like topography. I hope I said that right. Is that right? Topography. Okay, yeah. topography, right? And contour lines, right? So for local maximum minimums, you're gonna want to look for closed contours, okay, or something that looks like this. Something like this, okay? So this point over here is our maximum or minimum, and how do I say this? It goes up and down. Low battery. Okay. So this is our critical point. So it can either be a maximum or a minimum, and what these closed contours pretty much tell us is whether it's a maximum or a minimum. So it can either be increasing or decreasing. So if it's if this is a critical point and the height decreases, the height value decreases, or the function value decreases, that means it's a maximum, because you're starting up here and the function values on both sides start to decrease. So it'll look like a maximum or a concave down graph, right? However, if it starts to increase, that means we'll be at a minimum, something like that, okay? Where that was the critical point right there, like that, and we're looking at this cross section. Okay. So for if we classify it as a minimum or a maximum, if fxx is less than 0, then we're taking a look at a maximum. If fxx is greater than 0, then we're looking at a minimum. So it's similar to what we talked about before with the second derivative of one variable, of a function with one variable. If the second derivative is f double dash is less than 0, then we're taking a look at a maximum. If it's greater than 0, then we're taking a look at a minimum, okay? The only difference is that we can use fxx, or we can also use fyy. So what you want to do is, first of all, you want to find the critical point. So it will be in the form AB, right? And then you want to substitute it into our fxx and or our fyy function, okay? If it's less than 0, then it will be a maximum, local maximum. If it's greater than 0, then it will be a local minimum, okay? Now, the reason we can use fyy or fxx is because it's closed contours, right? So it doesn't matter which direction we cut it in, right? It will be the same, because it's increasing. The increase is like 1-to-1, if that makes sense. Okay? So that's local maximum or minimum. The next classification is a saddle point. So this is a completely new concept. So this involves open contours. So it might look something like this. Okay. Gosh. Right. So these 2 points are our critical points, right? And the way these open contours work is that one way will be a maximum direction and the other way will be a minimum direction. So rather than classifying it as one maximum or minimum, it actually consists of both, okay? So what's a good way to think about it? Think about it like a valley between 2 mountains. So if this was a mountain here, so if this was a high point, this was the high point, so a mountain, so you're in between 2 mountains and you're walking in between. So from a side view, this is a critical point, something like that, and you're walking into the page, all right? This is a minimum critical point, all right? And what I'm going to say, this is low, this is low. You're walking along the lower route. Okay. So that'll be a minimum, maximum, maximum. So that means if we cut it between here and here, that will give us we'll be able to find out a minimum critical point, minimum point, which is somewhere around here. Right? However, if you cut it in this direction, right? Cut it in that direction, it will, from the side view, it will look something like that. So it will look like a maximum point. Yeah, because this is a low point, this is a low point, and this point here is like a critical point actually. So this is our critical point, so that can either be a maximum or a minimum, right? And if we're going from a low point to another low point to a low point, but it travels through a maximum, it will be like a concave down graph, something like that. Okay. A little bit actually, a bit hard to explain, but a way to visualize saddle points is sort of like a Pringle. So let me draw it up actually. Yeah, it's nice actually. Yep, something like that. Yeah, something like that. So, as I said before, this direction is a minimum. This is our critical point. This direction is a maximum. So if we cut it in this direction, so we're cutting it, how do I cut this? Like that, right? From the side view, it will look like that. So you'll be able to see a maximum point. However, if you cut it through, how do I do it? Something like, if you cut it between this point and this point, like downwards, you'll be able to see a minimum point like that. Okay. Oh, if I had a photo, it would be so much easier to explain. No, I don't. Okay, that's fine. That's all good. Okay. Okay. But the main point is, for a saddle point, we're actually going to have to use a second derivative test. So using second derivative test. Okay. Oh, sorry. If you want to determine whether it's a saddle point or a local maximum / minimum, right? So there are two possible scenarios that we have to classify. We're going to have to use a second derivative test. So d is equal to fxx fyy minus f of xy all squared. Okay. Now, if this is less than 0, right, we're going to get a saddle point. And I'll explain why in a bit. If it's greater than 0, then we'll get a local max / minimum. Okay? Now, I want you to think back here. When I said we can use either fxx or fxy, oh sorry, fxx or fyy, if we assume that these are pointing in the direction of x and y, so they're aligned with the x and y axes, what actually happens is that this term becomes 0. Okay, so let's assume that this is 0, right, and it's aligned with the x and y axes, right, our local maximum and minimum directions. That means we're left with d is equal to fxx fyy. If it's less than 0, right, that means one of these are positive and the other one is negative. So this might be positive, this might be negative. That's the only way that we'll get a number that's less than 0, right? Right? Now, and okay, and as I've discussed before, for a saddle point, there's both a maximum and a minimum. So a minimum in this direction and a maximum in this direction, right? And we know one of these has to be a maximum, so this might be a maximum, and this one has to be a minimum, okay? So that's one way to tell why the saddle point has to be less than 0. And for a local maximum or minimum, if it wants to be greater than 0, that means they're the same sign, okay? Because this can also be negative and a negative. If it's both negative, that means it's still greater than 0, okay? And as we said earlier, for it to be a local maximum or minimum, they have to be the same sign. fxx and fyy have to be the same sign, okay? So that's another way to think about how the second derivative test actually works. But usually we always have to use the fxy squared term, okay? Because it's not always, these ridges are not aligned with the x and y axes, okay? Hey, the lecturer, he probably does a much better job at explaining than I do. But I'll try to go through a question here, okay? Hey, first step, we have to identify critical points. The way we do that is we have to find fx and fy. This is just minus 2x minus 6. This is just equal to minus 2y plus 4. And we said we have to let both of them equal to 0. Okay? Now this is pretty simple. We get x is equal to minus 3, y is equal to 2. So we found the x and y coordinates of our critical point. So coordinates of critical point. Critical point. Okay? So if we want to find the function value or the z value now, we just got to substitute it in. And blah blah blah, you end up getting 18. So this is the value of the function at the critical point. Crit point. Okay? So therefore, that means our critical point is minus 3 to 18. Now, so we found the critical point. Now we have to classify whether it's a saddle point or a local maximum / minimum. Okay? So this used the second derivative test. fxx is just equal to minus 2. fyy is also equal to minus 2. And fxy is equal to 0. Okay? So if fxy is equal to 0, that just means that the local maximum and minimum are in the same direction as the x and y axes. So now I'm going to substitute it into d. So this is equal to fxx fyy minus fxy all squared. This is equal to 0. And we can just substitute it in. Minus 2 times minus 2 is equal to 4, which is greater than 0. Okay? Therefore, we can say it's a local maximum or minimum. Okay? But we're not done here. We have to finalize and give a final answer whether it's a maximum or a minimum. Okay, we can say that since fxx is less than 0, is equal to minus 2, which is less than 0, right? The critical point minus 3 to 18 is a maximum point. Okay, so we've pretty much found the critical point and we've categorized it as a maximum point. Now, this step we don't have to do if we have a saddle point. Okay, so if this was a negative number, we could just say that the critical point is a saddle point. We don't have to do anything. We don't have to do any extra steps. Okay, and this is like a visual representation of it. So this is the 3D 3D plane, right? And this is the topographical view of it. I'm not sure how to say that. And this is our critical point. And as we can see, because it's a maximum, the function values are decreasing as we move along the x and y axes. Okay? And this is the maximum point here, the 3D view of it. Alright. They're pretty much always in this form. So if you just follow these 2 steps, you'll pretty much get every single question right. Alright, Lagrange multipliers, okay? Sorry. To find the local minimum and maximum of a function with a constraint. So what the constraint pretty much means is that, what does it mean? Let me think. I've got it in my notes. Oh, actually, rather than saying what it is, I'll explain why we actually have to use it. Is because in real life, there are actual constraints, if that makes sense. That doesn't make sense, actually. Hey, sec. I'll just explain how to do the questions. Okay, so I'll quickly explain a geometrical view of the problem. To formulate the problem, we need to first express outside of the condition in the generic form of g of x, y is equal to 0. After doing that, we're going to have to take a look at the minimum and maximum values of f, x, and y. So that's finding the critical points. And we're going to have to find the points that satisfy g of x, y is equal to 0. Okay, so I'm going to make a sketch. Z, Y, X. Okay. Let's say let's say this is a function. So this is our function. What is this? Z is equal to f, x, y. All right. And then there's also a function down here. So this is g of x, y, but it's equal to 0. Okay, because that's our constraint, that it has to equal to 0. So it lies in the x and y plane. Or we can say that z is equal to 0 for this case. Okay. Now, this constraint. Actually, no, that's not correct. It's not that z is equal to 0. Rather, because it's only in the because the constraint is only in terms of x and y, we can say that this function is true for all z values. That's a better way to say it. So we can actually extend this function infinitely. So dot 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 dot. Let's extend this infinitely this way. Okay, and what we can actually do is we can like make a copy of this function onto the function fxy. So it will look something like this. Okay. So we can make like a carbon copy of that function onto z is equal to fxy. Okay. And now, so, oh, that's actually not correct. It should look like this. Okay. Now, what we can do now with this, we can find max and min of this copied. I'm gonna call it a copied curve. Okay. Okay. And I'm gonna call the copied curve L of x, y, and I'm gonna also, because it's how do I say it? It's not only in terms of x and y, because we have the function z of fxy, and we've also got the function g of xy, which is also included into the function of L, but it's a, what is it? It's a multiple of the function of g. So I'll quickly show you what that means. So I'm going to first of all say it's in terms of lambda, x, y, and lambda. So it's 3 variables. So it's fxy plus lambda g of x, y. That's what this copied curve is. Okay. We don't need to get to the technicalities of how this is actually proved, or where this function, where this equation actually comes from. All we need to know is the steps to solving the question using this thing over here. Okay. So first step. So first of all, let's say we have Lxy lambda is equal to fxy plus gxy. By the way, if this equation doesn't make sense, don't worry, it's not meant to make sense. Okay. Okay. They're not going to ask you, oh, where the hell did this equation come from, right? They'll just ask you how to solve these type of questions. So step 1, we're going to take the partial derivative of L with respect to x and let it equal to 0. Okay, so we get fx minus g minus lambda gx is equal to 0, and then we get fx in terms of gx now. Okay, similarly, I'm going to do ly is equal to 0, so you get fy gy is equal to 0, and same thing over here. Okay, the third step is probably the most important one. We've got to actually differentiate with respect to lambda. So what actually happens is you get minus g lambda, minus g of xy is equal to 0. So that just pretty much just gives us a constraint. So what we're going to need to do is we're going to need to solve these 3 equations simultaneously. Okay. What that does, it gives us pretty much the values of the extreme points. So the extreme points over here, extreme points over here. Okay, so in this case there will be 2, because there's a maximum and a minimum between this constraint. Okay, let's take a look at this question. Find the extreme values of this, what is this? This equation, this plane. So it's a plane with the constraint of a cylinder. So similar to what we had over here. So this is like our plane, and we have a constraint of a cylinder. Okay, I'll show you guys a visual representation of what this is meant to be. Oh yeah, one note by the way, the question doesn't ask find the extreme values of z equals to fxy. Okay, so if you're trying to find the value extreme values of fxy, we run into a problem because it's a plane. It actually doesn't have a maximum or a minimum value. So it blows off to infinity and negative infinity. So yeah, he can't find the extreme values unless there's a constraint. So this is why they've actually given us a constraint. This is another reason why we actually use constraints in the case that we actually can't find any extreme values. So we're going to have to constrain the domain and try to find the extreme values within the domain. Okay, this constraint is essential as they've said over here. Okay, so this is what it actually looks like. This is our plane, and within the cylinder there's like a small disc that forms. Okay, and you're trying to find the maximum and minimum point. Okay, one more thing to note is that earlier to find whether it's a maximum or a minimum, we had to take a look at the second derivative. In this case we don't have to do that because we can just find the function value. Okay, because this is increasing linearly, right? We don't have to find whether it's a maximum or a minimum. We don't have to find it using the second derivative. I mean, we can find it much easily by just calculating the function value. Because this one, well, visually it's higher, that'll be the maximum point. And because this is lower, this will be the minimum point, okay? So, find the extreme values. I'll quickly show you how to do this question. So, fxy is equal to 12 plus 3x plus 4y. G of xy is equal to x squared plus y squared minus 1, which is equal to 0. Now, using these two equations, I'm going to form a third equation, Lxy lambda, which is equal to 12 plus 3x plus 4x, plus, minus lambda of x squared plus y squared minus 1. So what we have over here is just fxy minus lambda gxy. Right? So let's find Lx. That's just 3 minus 2 lambda x. The lambda we can just treat as a constant. Okay, that's pretty much all it is. It's just a factor or a constant. Okay, Ly is just 4 minus 2 lambda y. L lambda, as we discussed earlier, this cancels out completely. This just becomes 1, and we're left with g of x, minus g of x, sorry. Okay, so this is our constraint equation. Okay? Okay, we actually have to let this equal to 0, let this equal to 0, and we are left with what we have to do. Because our constraint equation is in terms of x and y, what I'm going to do, I'm going to find the value of x and y using these two equations. We get 3 on 2 lambda and 2 on lambda. Alright? This is just making x and y the subject. And I'm going to substitute these. So I'm going to substitute these into our constraint equation. So that's mainly what the constraint equation is for. Okay, we always want to use these two to find x in terms of lambda or maybe some other variable, and we're always going to sub it back into the constraint equation. Okay, in fact, you might even, oh no, that's probably in some harder questions that you'll see later on. Okay, so I'm going to substitute x and y, I'm going to get 3 on 2 lambda all squared plus 2 on lambda all squared plus 1, is equal to 1. You get 9 over 4 lambda squared plus 16 over 4 lambda squared. So I've made this actually 2 and 4 to make it a bit easier. And you're left with 25 over 4 lambda squared is equal to 1. Now we can solve for lambda. Lambda is equal to plus or minus 5 on 2. Okay. Now, what do we do with this lambda value? Okay. What we have to do is we're going to have to substitute this back into our x and y. Okay. So it's sort of like back substitution, right? So now we can find the values of x and y. X is equal to either plus or minus. Okay, what I'll do, so I'll just say, okay, no, I'll make it a bit easier. So I'll say for lambda is equal to 5 on 2, we get x is equal to 3 on 5, and y is equal to 4 on 5. Okay. And then for lambda is equal to minus 5 on 2, this is equal to minus 3 on 5, y is equal to minus 4 on 5. Alright. Now, as I've said earlier, so now that we found the critical points, so these are now the critical points. So this one and this one, right? So these are the coordinates. To find whether it's a maximum or minimum, we can just substitute it into the original equation. So 3 on 5, 4 on 5. We get this to be 12 plus 9 on 5 plus 16 on 5. And this is just equal to 17. F of minus 3 on 5 minus 4 on 5 is equal to 12 minus 9 on 5 minus 16 on 5, which is just 7. So therefore, 3 on 5, 4 on 5, 17 yields maximum. And minus 3 on 5, minus 4 on 5, 7 yields minimum. Okay. So first step, write it down. First step is find our L function. Second step is differentiate them with respect to x, y, and lambda. Third step, simultaneous equations to find x, y, and using this one over here as well. So this is part of the third step. Find lambda, and then you want to find the critical points. So this is finding the critical points, which is step 4. Finding crit points. Okay. And then final step, determine whether it's a maximum or a minimum. Okay. This is a bit of a harder question. I don't have time to go over this, so I'll skip over it. Do I want to go over this? Yes, I do. Okay, so given a scalar field phi x, y, z, so a scalar field, what is it? I'm not too sure. But the gradient of the scalar field is actually a vector field. Okay. So the way we actually convert between the scalar and the vector is using this what's it called? I forgot what it's called. Directive. No. Okay, it's called something. But to go from a scalar to a vector, a scalar field to a vector field, we're going to use this equation. It's not really an equation, but it's like an operation. Okay? So this is delta. I think it's delta. Alright. Let me check actually. Greek symbols. No, it's not delta. It's the opposite of delta. What the heck? Nabla? Maybe nabla. Nabla. Yeah, it is. Yeah, okay, cool. Nabla. So it's nabla. But I'll just call it the gradient. Okay? The gradient of phi is equal to this vector over here. So this is a 3D vector, which all consists of the partial derivative of phi with respect to either x, y, or z. Okay. Now, the gradient of phi at a certain point, all we have to do is find our gradient and then substitute the values of p. So p might be in the form a, b, c, and we're just going to substitute that in. And the notation for that is the gradient of phi with a line and a subscript of p. Okay, so this vector, the gradient vector, is pointing in the direction of the maximum increase with a magnitude of this. If it's a maximum decrease, then it has a, what's it called? It has a magnitude of minus. Okay. What else do I have to get? A directional directive. So all the directional derivative is the rate of change of phi at a certain point in the direction of a certain vector. It's very confusing, but what it is, you have to find the gradient at p, and then we're gonna use the dot product that you learned in 1A to find the gradient, to find the directional derivative in a certain direction. Okay, so what the unit vector does, it kind of standardizes it in a certain direction. Okay, so I'll show you the directional derivative in this example. So first of all, we're going to find nabla phi, which is a vector. Okay, so this is just equal to 2xyz plus x squared zj plus x squared y k. Okay. Now, at p of -1, 1, 3, we're just subbing our points into here. And you actually get the vector, after you substitute it in, you get the vector -6, 3, and 1. Alright? So this vector is pointing in the direction of the maximum increase in rate of change. Yes, that's true. Okay. Now, if we have b is equal to, so they want us to find the directional derivative in this direction. Okay. So we have the vector 1, 2, 2, and the size of this vector is just 3. All right. The way we find that is 1 squared plus 2 squared plus 2 squared. And therefore, our b hat, or our unit vector, is just 1/3, 1, 2, 2. Okay? That's how we find the unit vector. Okay. Now, the final step is pretty much just using the dot product. So we get -6, 3, 1 dot 1, 1, 2, 2 dot 1/3. I should probably put the 1/3 in the front over here. Okay, and what you get from here is you get 1/3 times -6 plus 6 plus 2, you get 2/3. So our directional derivative is equal to 2/3 at the point -1, 1, and 3. Okay. Now, pretty simple. What I'm going to do here, I'm actually going to show you guys a quick proof. Do we have time? Yeah, I do. Okay, so from Math1A, we know that u dot v is equal to the size of u times the size of v cos theta. Alright? Now, what if u is equal to this vector and v is equal to b hat, the unit vector? Right? What happens to this equation? Okay, what happens is that u dot v, first of all, this is where the theta comes from. Okay, u dot v is equal to pretty much just the directional derivative, right? Which is equal to the size of this vector. So that's one vector in the inside, times the size of the unit vector times of cos theta. Okay, first of all, the size of the unit vector is just equal to 1, right? And what we have over here is just the directional derivative, which we know points in the direction of maximum increase. Okay, one more thing that we can note is that cos theta has a maximum value of 1, and this occurs when theta is equal to 0. Okay, so if you want to find the max rate of change, because we know that this is the rate of change, okay, as we discussed earlier, that this is the gradient, which is also known as the rate of change. Okay, so the rate of change, so the max rate of change occurs when cos of theta is equal to 1. So this is equal to 1, this is equal to 1. All we're left with is this, the size of this. So our max rate of change we can just find using this formula over here. Okay. Now, for one more question, consider the scalar field. So that's our scalar field. If you want to find the gradient of phi, we're going to have to use this equation again. Which is equal to 2xzi plus 4y minus e to the z squared j plus x squared minus 2y e to the z squared of k. Wait a second. I'm figuring a z somewhere. Nah, that looks alright. YZ. Yeah, there should be a zero. Z here, sorry. There should be a Z. Okay, now at P, which is 1, 2, 0, we get that this is equal to 0, 7, 1. So you'll get the answer after you sub everything in carefully. Okay. Now, what they've asked us to find in this question is what is the magnitude and direction of the maximum rate of change. First of all, we know the maximum rate of change at the point P is just equal to the size of our vector. Which is just equal to root 50. So that's our magnitude, right? And it's always a positive because we're taking a look at the maximum rate of change, right? Bye-bye. And now, if you want to take a look at the direction, what we discussed earlier is that this vector is always in the direction of the maximum increase. So if we're taking a look at the maximum change, so if we found the maximum change, we know that it's in this direction, okay? So therefore, this is our maximum rate in the direction of 0, 7, 1. And that's our answer right there. Okay, doesn't get much harder than that, I'm pretty sure. Okay, one more thing I just wanted to touch on really quickly. Level surfaces, tangent planes, and normal lines. Level surfaces of a scalar field is pretty much the surface formed by all points and that has the same value as theta. Alright? How can we explain this? So you might have something like this: x squared plus y squared plus z squared, and this might equal to 25 as usual, or not as usual, but as we've seen earlier. And this is pretty much our level surface, because it's a surface formed by all the points that have the same value. Okay? Okay, no, that's a terrible way of explaining it. Okay, sack that. I want to take a look at tangent planes. I'm going to take a look at it, but if you want to find the tangent plane, you're going to need to find this gradient curve again at the point P, and then you just want to dot product it at the point x0, y0, z0. Let me think of the proof for this. So if you imagine it to be like a circle here, and that's our tangent plane, we know it's in the direction, it's in this direction, you know that, and this might be our point x0, y0, z0, and then this distance over here, I don't know, that's not right. Okay. Sack, I actually don't know. All I know is that they'll probably give you the formula, and all you have to do is sub it into the formula. Okay. Overall, this course isn't too difficult. There's just a lot of content, especially in the last 3 topics. There's a lot of content that they're gonna cram within 3-4 weeks. So I suggest getting what I suggest is getting the first few topics done really early. So that's what I did. I would finish everything up until matrices, maybe until flex week. But they actually take their time. They actually finish matrices really late. But then you wanna start maybe you can get it done earlier. Maybe in week 5 you can get it done. And then replace transform pretty much flex weeks onwards. I think that should give you a sufficient amount of time to work on it. Okay. I wasn't able to go through ordinary differential equations, but I'll try to post these notes up onto the messenger chat, and I might fill out all of these as well, and then before I post it up. Okay. I don't have anything else to talk about apart from what do I say? Good luck. Good luck for the next 10 weeks. I'm sure you guys will enjoy MATH2018.